Good morning. So we were discussing about aircraft design, and we have seen in the last lecture few components of an aircraft. And if I draw an aircraft, this is the horizontal tail and this is the elevator. There is a vertical tail, there is a rudder, and importantly there is a wing, and there will be flap, there could be engine, and of course you will have landing gear. These are the primary components you have, right? We also know this aircraft is primarily designed to carry passenger or a cargo from one point to another in a civil sense, right? So we have to also bother about what is there inside this fuselage, right? And also we know that somebody will be flying it, so there is a pilot, there may be more than one pilot, there will be crew members, we say. All those things are to be integrated in the design. There are requirements to be integrated in the design. Many times these requirements are conflicting. So as we develop, we will see how to handle these issues. As I have told you earlier, this course will focus primarily on the conceptual configuration design with more stress on the aerodynamic aspects, right? Once I say aerodynamic aspects, let us go back to our first course where we talked about airplane performance, and we knew that if a flat plate is moved with a velocity v, then it will have a reaction experienced, and one of the component of reaction is called lift, another component is called drag, right? As a designer, I need lift because I need to lift the weight. As a designer, I want drag to be as low as possible because this drag will try to reduce the speed, because after all, how I am getting the speed is through an engine which is producing a thrust, a force. So if I want this drag to be handled with at ease, I will always prefer the drag to be as low as possible. But in totality, most of the time we look for a configuration where L by D is maximum. Most of the time. Whenever I think of lift, and from aircraft, we know that the major responsibility of the wing is to take care of the lift, right? And from here also we know if there is an angle between the velocity vector and the plate, that will be responsible for generating the lift at a given speed, at a given altitude, etc. we know, right? And whenever we say the aircraft should produce lift equal to weight, when I'm flying at a cruise like this, that is, if you recall your performance lecture, you have these two popular equations, lift equal to weight and thrust equal to drag. If I see here, first equation, lift equal to weight, how a designer will see this condition lift equal to weight? Why? It is an important question. I need to have an airplane, I need to have a wing, because we have agreed that lift is primarily responsible for generating lift. So I need to have a wing specially designed so that it can generate lift at different altitudes, at different speed, as per our requirements. Here also as a designer, when I see lift is equal to weight, so if I can somehow minimize this weight without compromising the volume, because after all we have to carry cargo, passenger, etc. And if somehow I can reduce the weight means what? Reduce the aircraft empty weight. Somehow if I could reduce this, it will help me. My conditions will be lesser taxed. So if I now try to see a little more through this equation, what do I see? As a designer, when I write lift equal to weight, I have weight and lift, these two aspects. One is primarily aerodynamic driven, which is the lift. This is aerodynamic driven. And this weight is basically material, then payload, etc. driven, right? Why weight is important? You'll find aircrafts are categorized by their weight class, right? So below 700 kg, below 1500 kg, like that, one characterization will be there. So weight does play an important role, so that there is a need to characterize an airplane one way through weight. Why weight is important? Let us see this. If I use thrust equal to drag and lift equal to weight, I know that thrust required will be W by L by D or W by CL by CD. So you could easily see that thrust required for a cruise flight, this is cruise, is directly proportional to the weight you are carrying and inversely proportional to CL by CD. So here, a smart aerodynamic person or smart aerodynamic approach will try to ensure the CL by CD is maximum, and a person, an expert who are on the material side, they will try to ensure that the weight is low. However, the primary objective of carrying capacity or carrying payload, etc., then the strength also comes. Very, very important. You need to have particular material or particular composition, a particular combination of material to ensure that it is enough strengthened to counter the stresses developed when the airplane moves in medium, which is air in this case. So you could see that this is very, very important if I want to ask myself how much thrust is required for a particular mission requirement. Let's say you want to design an aircraft, there will be some mission requirement. We will talk explicitly on mission requirement, but to start with, what could be mission requirement? That you say, okay, my airplane should be able to climb up to an altitude of 10 kilometer, 11 kilometer. My aircraft should be capable of cruising at that altitude with 150 meter per second, 100 meter per second, and if it is high speed, it is 300 meter per second. Even then, it can go up to 1.52, depending upon what way you are designing. But if you recall, I have mentioned that initially we will be talking about low speed aircraft. So I need to know this weight, because that will tell me what is the thrust required, and I can now think of what sort of an engine I will be picking up, right? Also remember, I have told the engine part will be almost like we are taking things from the shelves, right? Standalone engines are available. We are not going to design engine in this course at all. So weight is that way extremely important. And second part, as a designer, you need to also look here. When I say lift equal to weight, lift I know half, rho v square S CL equal to weight, right? Rho is what? Rho is whatever altitude you are cruising or taking off. This is of course for cruising I am talking about. CL is the lift coefficient, and of course W is the weight. And if you see here, the speed required to maintain lift equal to weight will be given as 2 W by S by rho CL. So from this cruise condition we find that whatever altitude I am flying, I need to have enough engine thrust or power so that I can attain this much of V, and that V is proportional to W by S. It is inversely proportional to density, inversely proportional to CL, or CL to the power half, or to the power half in particular, and if I write it here, also to the power half. So if I want to cruise at a speed which is lower so that my engine requirements are less, what option I have got? Then I must, if I want to really see that V cruise which ensure lift equal to weight, if I want it lower, that means I have to ensure that W by S is also low, CL is higher, and rho is also higher. Just directly from here. As far as rho is concerned, that is not in our hand, because depending upon which altitude you are flying, rho will change, right? Now there are two things. One is W by S, another is CL. These are two important parameters which we need to understand as a designer. And one is W by S, which is primarily the weight by wing area. And this is primarily aerodynamic. And this W by S is known as wing loading. So I write lift equal to weight and half rho V square SCL equal to weight. I write V equal to 2W by S by rho CL under root. This is the speed required to maintain lift equal to weight at an altitude rho, which is flying at a given CL. But when I talk about wing loading, please understand this. This wing loading has a clear cut. The wing loading needs to be clearly understood, because there is a generally confusion I have seen among the student. When I say W by S is the wing loading, I am assuming lift equal to weight, right? But you can see that airplane can also fly such that lift equal to NW, having a load factor of N. In that case, wing loading or V required to fly will be 2N W by S rho CL, and you could see that if I write this as 2 W by S star by rho CL, what I am seeing, the W by S star is nothing but NWS, that is the wing loading has actually increased, right? One is going for a load factor N. So whatever wing loading we talk about, we are clear back of our mind that we are talking about lift equal to weight. That means if you're designing an airplane for a mission and you have chosen W by S some number, you should not expect that number is good enough to do a maneuvering flight, where the wing loading required is W by S star, which is nothing but n W by S. As if the weight has increased by n times, right? You could easily understand, if I go on increasing the wing loading, meaning thereby, what does it mean? If I go on increasing the wing loading, that means I am reducing the wing area. For example, if I have a mass or weight W, I flatten it, and let's say W remains same and area is S1. Second case, same thing, but I flatten it further, and that time the area is S2. The first case it is W by S1, second case it is W by S2. The wing loading W by S2 is less than wing loading W by S1. The moment wing loading is less for the second case, you could see the speed required to maintain level flight is also less. The wing loading plays one of the important role in deciding the speed for a given CL, right? We'll further see what this wing loading actually means to a designer. You are aware of Vstall. We have talked about Vstall as under root 2 W by S rho CL max. You also know CL max from other two courses. This is CL versus alpha. If I plot it like this, somewhere there is a alpha stall, and this gentleman is CL max. Typically the CL max value for the average side, if I say for a conventional wing without any flaps and all, it's not a bad idea to take that value as 1.2. Okay. Now see here. What is Vstall? Vstall is the minimum speed required to maintain lift equal to weight. Right? So let's have an idea. If W by S is increased, what will happen? Vstall will go on increasing. Similarly, if rho goes on decreasing, that is, I am taking off in Kanpur, then taking off in Leh and Ladakh, the Vstall also will increase in Leh and Ladakh for same W by S or CL max. That is, for same W by S and for same CL max, if you want to fly with a minimum speed lift equal to weight, that will be higher compared to in Delhi or Kanpur, because rho is less in Leh Ladakh area. Let us see, let's have a feel for number. Let us see, W by S is 10 kg per meter square. Please understand, this W by S unit to be consistent should be Newton per meter square, right? Because lift equal to weight, so this gentleman is in Newton, so W also has to be in Newton, right? But I am writing W by S as 10 kg per meter square, and if rho, if I take it is 1 kg per meter cube, and let's say CL max, I am taking again 1.0. Just to make life simpler, what will be the Vstall? Vstall will be 2 into W by S, that is 10. This is kg per meter square, so I have to multiply by 9.8 to convert Newton, and rho is 1, and CL also I have taken 1. So this will be around, let's say roughly I take this as 10, 2 into 10 into 10. So I am approximating 9.8 equal to 10, just for calculation purpose, divided by 1. So this will be 10 root 2. So this is 10 root 2 and root 2 is 1.414. So this is roughly 14.4 roughly, let's say, meter per second. And what is this 14 meter per second? As a designer, how do you visualize what is 14 meter per second? Because mostly we have got a feeling in terms of kilometer per hour. So 14.4 means roughly 14.4 into 3.5 to multiply. This will give you kilometer per hour, roughly, right? So around 50 kilometer per hour, right? That is the speed. Now see, if I increase wing loading, in this case wing loading first was 10 kg per meter square. Now suppose I raise this wing loading to 40 kg per meter square. This 40 kg per meter square is the wing loading typically for motor gliders, right? We have shown you the first lecture, the sinus 912. This is typically the wing loading. So if I assume other things are okay, other things are good enough in approximation, then I will get V stall as under root, let me write it here. So what I am saying is W by S is 40 kg per meter square. So V stall will be 2, W by S is 40, again into 9.8 to convert to Newton, rho I have taken 1 and CL I have taken 1. Please understand CL typically is 1.2 maximum you get. For V stall you need to take CL max, but we are taking it 1. And this also now comes out to how much? How much? 28 meter per second, which is equal to, just multiply by 3.5, 98 kilometer per hour. So 98 kilometer per hour, you understand, if you drive a motorcycle, it's almost 100 kilometer per hour. It's a huge number, right? We'll see what happens if W by S becomes 100, which is typically passenger, small business aircraft. The order will be around 100, small, 2-seater, 3-seater. If W by S is equal to 100 kg per meter square, then what happens to V stall? Again keeping density and CL, whatever we are using earlier, this will be 2 into 100 into 9.8 by 1 into 1. This will be how much? Can we just check? 44.3 meter per second. That will be how much? 155 kilometer per hour. So you could easily see that as I am increasing wing loading from 10 to 100, the stall speed is changing from around 14 to 44 or 45 meter per second. Most of our airplanes, Cessna, Saratoga, all these things, there will be, V stall will be around this, right? This number has a meaning, you will understand. If I now go to typical aero model, for aero model, W by S is right, order of 1 kg per meter square, smaller one I am talking about. If it is 1 kg per meter square, typical aero model which you know, it just takes off, what will be V stall? V stall will be under root 2 into 1 by into 9.8 by 1 into 1. This is how much? 4 to 5 meter per second. That's why it is so easy to fly such machine. When I am saying V stall from 4 to let's say 100, and for a bigger airplane, this W by S will become 300, 400, 500. So you could see the V stall will go on increasing. And the increase in Vstall means what? Vstall means minimum speed required to maintain lift equal to weight. And who will ensure this Vstall? Who will ensure that yes, the airplane is moving with, is capable of flying with this much of speed, this or that? What do you require? You require, this is the airplane, you require the thrust or the power should be capable enough to overcome the drag experienced by it so as to maintain the speed which we are demanding. If this number is more, it means you need a high power engine. That also means the weight of the engine will increase. The weight increases means again you see your wing loading will change. Everything goes into a iterative mode, right? But as a good designer, you should understand what are the implications of wing loading. There is another observation which a designer need to have priori on wing loading is, if I increase wing loading, that means relatively the area of the wing I am reducing, right? If I want lesser wing loading so that Vstall is less, for lesser wing loading, S is relatively should be higher for a given weight, right? What is the implication of S being higher? S being higher means larger area. That means larger area. Okay, that is good as far as lift is concerned. But what is the problem? As there is a larger area, that means the drag also will increase, skin friction drag primarily, right? So that means if drag increases, that tells you you need more thrust or power, right? So you could see that there are conflicts. A designer has to satisfy everybody, and depending upon the mission requirement, he will satisfy one aspect more than the other. For example, if it is a fighter airplane where I need larger maneuver, I will not fly at a smaller wing loading. I will fly so that wing loading is low. So if wing loading is low, I can accelerate fast because the drag part will be less. Okay. And also, if wing loading is low means relatively the wing is smaller means the airplane is compact. So I can roll very fast. If the wing is very large, rolling will become difficult. Right? So all those conflicts will come. But we need to know we should be able to smell a wing loading. If a number comes to a figure on your table, this wing loading is this, immediately you should know that, oh, this has this has that, this will have this problem, this will have disadvantages. That is why I am revising few concepts like wing loading, etc. After wing loading, this is another concept we will be talking about. We will be going in detail about wing loading and all in each lecture. But before I go for those lectures, I just thought I'll revise few things. There is something T by W. If W by S is wing loading, what is T by W? T by W is also some loading, but this is thrust loading. What is the implication of thrust loading? For example, wing loading, we have seen wing loading has direct relationship with the Vstall, minimum speed to fly level, lift equal to weight. Thrust loading, if you want to see, again you have to go to your performance lecture where for a steady climb, we call the diagram. We call this diagram that we are flying. we're flying such that it is climbing at a climb angle gamma. So gamma is the climb angle. And we have explained about steady climb. For a steady climb, I can easily write T minus D minus W sine gamma equal to m dV by dt. Since this is a steady climb, so we equated this equal to 0. That is climbing at a constant speed like this. And now if I see this equation, I can write T by W equal to sine gamma plus D by W, which I can approximately write equal to sine gamma plus 1 by CL by CD. This part is approximate. I am assuming lift equal to weight. But here you could see lift is not equal to weight. The component, if we see like this, lift will be W cos gamma, but I am assuming gamma small. So I am taking the liberty. Just for a designer, he does lot many approximation to get feel for some number. Now this equation is very, very handy for a designer once he wants to know what should be the thrust loading. Typically CL by CD may be around 10, around 15, depending upon what type of aircraft you are designing. So even if it is 10, so this contribution will be at most 0.1. Because CL by CD will be more than 10 actually, you will find 15, 20. So this component will be at the most 0.1. And this is straightforward. So how much T by W you require? Sine of, if I want to climb by 30 degree, so this is 0.5 plus 0.1, 0.56. Right? No, 0.6. This is 0.6 because sine 30 is 0.5. If I am climbing at smaller angle, accordingly I know what is the T by W required. Because thrust is primarily required for climbing. For cruise, the thrust requirement will be much less. Because in the cruise, thrust will try to only balance the drag of the machine. But while climb, it will not only try to overcome the drag, but also take the weight upward. Please understand that when I have written here D by W, and D by W I have approximated as 1 by CL by CD, that means I have assumed W equal to lift, which is an approximation where clearly you know that L equal to W cos of gamma. Right? Okay. We have just the designer, we know that okay, gamma around 15 degree, then cos gamma is almost 1. So some sort of approximation we have done. For analytical solution, of course, you should find out exactly by putting these values. So that should be kept in mind. But from designer perspective, please understand that this value CL by CD, we will be flying at a CL by CD much higher than 10, 15, 20. So the designer, okay, maximum 0.1 this one. What is our aim? We are trying to find out what is the T by W rough value I want. Who dominates it? We could see that it is dominated more by the climb angle. So directly from here, if I want to climb at 15 degree, sine 15 plus this value add, roughly you will get the value of T by W for your mission. Because you know that T by W is important for climb phase, because thrust required during climb is much more than thrust required during cruise. But there is another catch point you understand when I am talking about T by W and W by S. That is also a designer need to keep back of his mind. So you are loosely talking about, very, very loosely you are talking about wing loading and thrust loading, just to give you a understanding introductions, because we have to go in detail about those things in the design. But one thing you understand that as I am going higher and higher, the W will go on reducing. Do not forget that, okay? Similarly, as I am going higher and higher, even if I maintain same thrust, if it is okay, but W will go on increase, so T by W requirement will go higher, right? Then there is another thing, as I am going higher and higher, the thrust will also drop. Dynamic thrust will drop. If it's a propeller-driven airplane, you could see that density of air outside will reduce, right? So the thrust available from thrust or power, when you talk about propeller engine, you know that we talk in terms of power, and thrust means jet engine. So T by W, as I'm going higher and higher, the thrust part also will vary with altitude. So as a designer, I need to know how much it will change and keep that as a margin, right? So it is always better to have excess margin on this. So all those points also we'll be discussing. So for today, just for introduction, we have just glanced through W by S and T by W. And I will request you to go through my earlier lectures on performance and come prepared for next lecture.